I start recording. Okay, first of all, sorry for the delay, but I was finishing like some work at home, and then I forgot that this room, the new room where we are, doesn't have anything, so we needed to set up the projector and everything. We were in the rich one last time, but now we have the bad one, so we needed to take what we have. So I think, well, we are ready to. Well, I'm ready to get your question. I know that at least from Sichen and Enrique there are several questions, so I think we should start, also because it's already rather late. So I will share my second desktop, and I'll also just open a terminal so that we can go to see directly on the slide, on the terminal what we have. So now I put it here, view. Okay, so any news, by the way, from the IT people, Mariam? Because yesterday I saw that there was a conversation. Did they tell you anything?
Actually, they asked for my computer ID and this kind of thing.
Okay.
And just still waiting to see what's really going on.
Okay. So.
But I see that the firewall is on my computer when I was searching for the ID of my computer.
Okay. So you see that it's on. Good. So it means it is that one. Good. So they should then try like solve it.
Yeah.
And since we are now doing like a short break this week, then maybe for next week we have it settled, and then you can also do some exercise.
Yeah.
Next week. Okay, cool. So let's start. First question. Any of you? Why now? Okay. Good.
Okay.
Yeah.
The one I can start.
Go ahead.
I have a question. Apart from the hands-on, sorry, I have a question from the VASP project. But if you want, I can do it at the end.
No. Go ahead.
Okay,
I think we can mix without any problem. Yeah.
After that, just a couple of questions.
Yeah.
On the song, and today I think I'm going to be fast.
Uh-huh.
If you could go to the first bash script, the one that
Yes.
orders the postcard,
Uh-huh.
could you cut or maybe with BI both the input and output?
Okay, so yes. Well, actually, what I can. Do you want to see?
Sorry.
Do you want just to see the difference, or you want to see? You need to see both of them, because if you want, we can just focus on the difference. Well.
No, I wanted
to see both. Okay. So this is the input. Okay.
The first question, it's a simple question. I think that the answer is yes, but the idea is that every input file will be disordered, but the first ones will be with the first type of atom, and the second ones will be with the second one, and after that they're going to be disordered.
Exactly.
That's the idea, right?
So the point is that the idea is the following, as you said, that usually what you get out from like any crystallographic database is a component, the bulk, and from the bulk you get the surface. But the problem is that the surface is never ordered.
Okay.
So you will get something like that. You will just get like maybe it's ordered on the like y-axis or x-axis, but it's never ordered on the z-axis.
Okay.
And the problem is that you need to fix that, because otherwise you will need to see every time, okay, this is in the top layer, then I free it, this is in the bulk, then I fix, okay? So that's the problem. So the problem is an intrinsic problem of the generation of the input, okay? Yeah.
This is a concar.
So the point is that you can have a postcard both in Cartesian or in direct coordinates.
This is concar.
This is a postcard. This you get as an input, and you need to order because you need to run a simulation on this at home.
If it's a postcard, how could the lattice with a number so exactly?
What do you mean?
Look,
this.
The 11.45. The postcard we do that with our hands. So how could that be?
No. The postcard you don't do it with your hand. The postcard in this case, this postcard is a surface. So you take it from the database. So the fact that so far for the molecules or for the bulk, was very ordered is because we were working with molecule and bulk. But next week you will see that with surfaces is much more like that, you know, that you see like this 839, 1145, because I mean the surfaces are not that well cut as your bulk. Okay, but this is still a postcard. So this is still an input for your VASP simulation that you need to order in order to make it ready to run a simulation on that. Okay.
And you have put below the paradigm.
I mean, yeah. So it's not that I put what they do in order to, so like, as you know already, what you do in the postcard, you have the elements and then you have the number of atoms. So since VASP want to make it like saving space, then you put one element before and the second element after. If you prefer, you could have put one indium, one palladium, one indium, one palladium, one indium, one palladium, but then you will have like a string of 1, 1, 1, 1, 1, 1, 1, and so on until the end of the atom. And this is much more ordered. So you will always get this. You will always get the elements grouped, well, the atoms grouped by elements, but never ordered. Okay.
Okay. But
group by element for sure. Yes.
Okay. Yeah. And the second question, if you can go to the order 5.
Yeah. Okay.
I understand, but it's because I and my lack of knowledge about postcards. How well we cannot see.
Yeah. No, but I will just zoom out a bit more, and then I will reduce this, and then these things, I don't know why it's just happening all the time. Okay, now, because I need to close the chat. Okay, yes.
Let's, for example, focus on the first 16 one. I don't understand why, yes, we are ordering by the z-axis, so with the levels, but why it's like we have like first 8 of them and after that 8 of them. That's why I don't understand.
Yeah, why? Because I did this script very, very fast. I mean, this, I generate the ordered one myself, okay? And I did it very fast, so that, as you see, is suboptimal. I mean, the reason why you see that is because probably in the script that I did, like there is some parameter that I didn't change. So this script still like does it like that, you know, that like it's taking, I don't know why, the first 8 atoms is ordering them, and then it's taking, but this is like a bug of the script. So you see, like, I mean, the point is that it's not a tremendous bug.
Yes.
Because, you know, it's still like ordered, the final result will be the same, but indeed, like, it's not as good as it should be, because as you said, it should be like all the false and then all the true. Okay?
I was thinking that was for some reason.
No. This is just a bug.
Okay, perfect.
And that is a general like comment to all of you. Like in all the script that I gave you, they can be optimized. I mean, there is always a way to make a better script. So if you can do it better, just do it better. Just do it better. If you can make it faster, do it faster. Don't take my suggestion as the best suggestion. Okay? Yes. Then.
Okay, perfect. And after that, working with the hands-out too. Well, I have not done pretty much, but when I took the loop in order to take all the data and optimize the lattice constant, when I got the Excel, you were doing like an Excel of like an example. You were introducing yourself the values the last day, but the Excel that you generated from the loop, in my case, it's like it has the different values of lattice that we are trying and 3 columns.
Yeah.
That's right.
So here we go to the other, well, not the other problem, let's say, but the other limit of this Anson, okay? Because this loop is given by the Anson itself, okay? So it is not the best loop you can get, because as you see in the loop, you see that like I mean, it's not the problem of the script, because the script is just doing the best that it can do. The problem actually is on the script itself, because what you see here, what you're asking the script is just to print, so this tail minus 1 obstacle is just to print the last like things of each obstacle. So if I do this, well, now I cannot because I don't have the obstacle, but if you do that with a obstacle, you will just see what you have in every line of the summary, okay? So for instance, you can play with that, and you can think that perhaps instead of having these, you can have this graph, space, W, energy. And then you can also play, and here I will show you directly the result. What you can also play with when you do this is, so let's say, now we are, okay, no, it's not this one, I need to, okay, now.
So now, maybe wait a second, because if I have something to put below the things, then it's better, because then at least we don't see it. Because we see.
Yeah, I just want to tell you.
Now okay, now it's a bit tilted, but I think it's still better. Okay, so let's go for instance on this T1. Yeah, as Enrique just said, the problem is that what you get is exactly this.
Okay, yeah,
so this is just the last line of the Otziker. So if we do like tail -1 Otziker, you see that this is the last line. Okay. No magics there. Of course, you can improve the script if instead of having this graph, well, tail -1, you do like energy. So if you do something like this, here, for instance, you already take the energy, but of course you don't want all this line. You would like just to get this line. So in order to do that, you can apply another command that is this one. You know? Yeah, like there is a way that is the following. If you do like this command, allow you to print. Yeah, this is capital. I didn't see. Yeah. So what this command does is just printing like one of the columns. So in this case, I'm printing the third column, okay? So then you need to play a bit with that in order to go to the column that you want. So maybe 7 or 8. Yeah, it's 7, okay? So like if you put this command in the loop, instead of this tail, instead of this, then you will get these two columns that I mentioned, okay?
And also you can play with tail and AWK.
Exactly.
Okay.
So the problem, I mean, as I said, and this is a standard approach, you see like from here, you still get the minimum lattice vector, because what you do, you can just go to Excel, you copy everything, then you take this column or this column. I mean, it doesn't matter because this is not exactly the energy for sigma that is equal to 0, but there is an offset between these values and the one that we are printing with tail -1. So at the end, forgetting the lattice vector doesn't change because you're still getting the minimum. So let's say the parabola is just shifted, okay?
Yeah.
So
yeah. So you are using F. Are you telling me to use F, or because I was using E0, thinking that it's the correct?
No, I mean, like, so you see, like, I never try, but I think that again there is a offset between the two. So I don't think that you will see any difference. If you want, we can just check it very quickly. You know, so as I was telling you, like, what you can do if you don't want to do that, you just get like to all your value, and then you go here on Excel and you just do a plot. Now let's see, for instance, if these two won't correlate, and I think actually they will perfectly correlate. Well, I actually make the graph here. Yeah. No, but I want to see if like the F. Yeah, you see. So Enrique was using like this column, I think, and instead I told you to use this column, and as you see, there is a perfect correlation. Okay, so like you can use either of this column, not this one, because this is the delta E. Okay, and indeed, as Chen just said, what you need to do is to take the lattice vector and this one. Okay, but that was just to prove that either you take this one, or you take this one, or you take energy for sigma that is equal to 0, you will just see this. You see the linear correlation. So that means that, like, forgetting the minimum lattice, well, the best lattice vector is the same. Okay?
And I mean, and I have some question about it, because in the postcard, maybe we just the first lattice, the length of lattice. In some case, we just put 1, and I think that is enough for so much calculate about the catalyst. And why in this case?
Okay, where is the folder? Give me the example of the folder so that we open the folder. They also see.
For example, the first one.
Okay, so.
One FCC.
Okay, so I go to this one here. I think, yeah, you don't have a postcard because the postcard is inside the loop. Okay, now. So this is not one, eh? I mean, this $I is going between this one.
Yeah, I know.
So let's go, probably is another example. So let's try with the 2-4. I think is the one that is relaxed. Okay, let's go with the postcard.
Yeah, 4, 5.
Yeah. So we were talking about that yesterday with Enrique, and I think it's good to tell everyone. Okay. So this
is the lattice constant, and the coordinate of your lattice vectors are the following, because we are working now with FCC. Okay, and now we will try to show the same things that I showed yesterday to Enrique, that it took me a while to get it, but at the end I finally managed. Okay, crystalline. Okay, now. So before I will look for that, and then I'll show you, not to make mistakes. Okay, yeah. Oh, that is actually, yes, that is actually rather good. That is better than the one that I showed. So, no, okay, it was better to go directly to the, wait, because I mean, it was better just to take, let me just see, and just check here, even if it's not too big, it's too good. So, this is a face-centered cubic crystalline structure. That is the one that we are using, okay? So, the lattice vector is this one, okay? So what you are doing now, the cell that you are simulating with VASP is this one given by these three red vectors, okay? The lattice constant, so the one that we saw in this case was 5.5, is the distance between these atoms and this atom, okay? So the reason why you see in, and then we can go back here. So here you see 5.5, that is this distance, okay? And then as the lattice vector, you see 0, 0.5, 0.5, because you see here that, like, well, probably, I mean, it's not that easy to see. Like, I think it's probably this case, well.
Maybe that green one.
Yeah, but this is about the center, so it's a different one. Like, yeah, you mean?
Green one.
Yeah, okay, yeah, we can also take this one, yeah. So, like, yeah, basically, like, the lattice vector is here, you know? So you see why, like, since you're starting from here and you go from here, like, the coordinate of your lattice vector will be 0.5, 0.5, 0, because you are on a plane. So one of the three, like, x, y, z coordinate need to be 0, and the other two are 0.5, 0.5, because the position of this atom will be 0.5, 0.5, 0, okay? So that's the reason why you see this. And you always have this 5.5, and as I was telling yesterday to Enrique, it's exactly the same to put here 5.5, 0, 0, 5, 0, 5, or to put here 1 and put 0, 2.25, 2.25. Okay, this is exactly the same, because what VASP will do is just to multiply this by, like, the lattice constant by the lattice vectors, okay? Good. So, any more point?
Well, I just wanted to ask then, what's the meaning of F in those calculations that we were taking with one context?
Okay, then we need to open the Otziker, because I don't remember. And if we go to the Otziker, okay, then, yes, what you see, it's reading file, okay, okay, the first value is
Total free energy.
the total free energy, is point the energy of the reference atom is the, and okay, yes.
Okay, but why the idea is to use F, not E0? That you told me that they have a correlation and it doesn't matter, but why you were choosing F?
No, we are always choosing I mean, so we are always choosing E0, because E0 is the energy for sigma that tends to 0. Okay, this F, I mean, actually, like, as I say, like, in this previous, like, script, I just use F because I was just interested to get the minimum. But I will never use F if I need to have a proper estimation of the energy of my system. You know, because to have a proper estimation of the energy of my system, I need to go to E0. Okay? Good.
Okay, and my last question is about, well, I have not arrived to that point of the handout, but what I didn't understand pretty well yesterday is, yes, I understand that we are making simulations in order to see the density of states, and different simulations in order to see better the band gaps, right? But which is the difference? The difference is in the key points, the difference is
exactly. The different, there are two different, we can just check the things, okay? So we can, for instance, check the difference between, like, the two DOS, then the 2, 3, and we take the difference between the incar now, okay? Just to see which are the different. So you see that, like, the first difference that we have, the one on the top
is, I think is the first one. Let's check because I forgot the usage of this. So, let's see. Okay, yeah. So the only difference in the key inker is that on the DOS, you are using the tetrahedron method. So you're using this interpolation between key points, while on the bandgap, you don't. Okay. And I think that you are doing that because you are actually you are doing that because you have a completely different system of key points. So I think that the choice of the inker in this case is not because you want to optimize the DOS, because if you remember, it was suggested to have is mere equal to -5 for any electronic calculations, also for the bus, for the it's also for the band structure. Sorry, I got confused by myself. But the reason why you are using the tetrahedron method in the DOS and not on the band lies in the key point mesh. Because you see that for the DOS, you're using the Morse code pack, so you have plenty of key points, while on the D band, you are just using 10 key points. And you see also that you are giving the position of the 10 key point. But why? Because for the band structure, you really like the band structure is about like the different level for the energy of your electrons at given key point. So like while on the Moscow pack, you're more interested in the mesh, here you're interested on like, let's say the path of the key point. So here you are defining different like coordinates because you want, let's say, your calculation to be centered in some of these points that are the relevant one for calculating the band structure, and in the other case, no. And then I think that the other difference, and we can check it very easily, should be also on the final number of key points that you have. So for instance, if we now enter and we grab, like, should be enough key points on the out card. Why doesn't? No, because I'm not entered yet. No, because you know, whenever you do whenever you're just writing a script, I forgot. Like in this case, I'm not yet inside the folder. Okay, so it's good. Okay, so it's not this to get the key points. I mean, I get something, but not what I want. Okay, yeah, no, it's this NK. Okay, so NKP. Wait. Is okay, 2.3, 2.2, and then we get NKPTS, NKPTS. Okay, yeah. So you see that actually what is happening, because let's say you give like the position of the key point, but then like still like VASP is internally optimizing it in order to get the irreducible key points. And you see that actually in the case, well, we can also print the name of the script so that you see what we are talking about. So you see that for the DOS, you have 286 key points in the Brillouin zone, while for the bandgap, we have 40 at the end. So we set initially 10, and then VASP internally like organized it so that it got to 40, okay? But still, you see the difference. So the difference why, for instance, the density of state here is really bad, and here is not, is because our mesh or our density of key points is much lower. Okay. Even though we have the same, here we have exactly the same system. So remember, the Brillouin zone is the same, but since you have much lower key points, that means that you have basically like very, very low density of key points, okay?
Okay, and last question,
yeah.
When you are defining 10 key points by 10 on the file of key points,
yeah.
I think that there are just 8 key points defined with coordinates defined.
Okay, yeah.
Yes, but if there's symmetry, there should be some different way. So why the two lacking key points, how we are defining them?
Yeah, that's a good question. Okay, so I think there should be, okay. You need to check the way that they are defining.
If there's some symmetry, I think that the weight should be different.
No, but the point is that, so they had 40 at the end, no? And here they are, as you say, setting 8. So like, shit, yeah, that's true, because now we are 3.
So, okay, it doesn't matter. So in like in 10 minutes, we will run out of time because usually in a 1-by-1 meeting. But anyway, like in the case, I will start again a new Zoom for Santiago and Mariam. So I think the problem is this in this line, you know, I need to check the way that you are given like this automatic key point, because as I say, like you basically will never use this because you will never really calculate band structures with VASP, but it's still an interesting question. So let's see how they define the key points, the one that you, okay, string of key point. Okay, so it was my bad, okay, in the sense that like you don't define the number of key points. So this line for the band structure is not the number of key points, it's the number of intersections, okay? So the first line is treated as a common line, and the second line you specify the number of points per line segment. Okay, so 1, 2, 3, 40. Okay, let's see, because line segment means that one segment, two segment, well, one segment, yeah, two segment, three segment. The general strings of key point connecting specific point of the line one, the first non-blank character on the line must be, okay, line mode. Okay, so I guess that like here we have 1, 2, 3, 4. Okay, makes sense. So now we have 4 segments. Okay, so let's say it better. I think it's here is good if I annotate something. So what we are doing now, we have like 1, 2, 3, 4 key points. Okay, because we are starting, let's say, from L. Then we go on G. Then we go on
W,
yeah, this one. Then like this, and then from this one we actually go back to this one. It's something like that. Okay, so we have like 1 segment, 2 segment, 3 segment, 4 segment. 1, 2, 3, 4.
Sorry, that LG,
yeah,
they are bands.
These are specific position in the Brillouin zone. Okay, so in the Brillouin zone there are like different positions. So the center we say that is called gamma, so this G, and then the other are specific point, and depending on the point you get different. Well, you can get to know different properties. Let's say, okay. And so this line, this 10, is not the number of key points as I said before, but is actually the number of key points per segment. So here you have 10 key points, here you have 10 key points, and here you have 10 key points, and also on the last one. And so the sum of all these make 40. That is the one that we have. Okay, so now we clarify.
It means interaction.
Huh?
10 means interaction.
10 means the number of key points on this segment. Okay, because the definition is that this 10 is the number of key points on this segment. Okay.
But I still don't understand why we are defining 8 coordinates. Well, 8 parts of coordinates.
Because you are repeating some of them. So like now, you know, if you see this one and this one is the same, and this one is the same, and this one and the G is the same, because you are defining segment. So if you define segment, like you need to repeat. Let's say the problem is that I think that like VASP need to have the 2 point close.
Those 2 first are LG.
Yeah, exactly. And then you see, so this is LG, this is GX, and this is XU, and this is K, because it's a new one.
We are defining the 4 segments.
Exactly. Here you don't define the key points, you define the segment. Exactly. Okay? Good.
But how could I define this? I mean, the number of the area segment.
I mean, it's not that you define the number. Like, if you go to the Kittel book, you look where is the position of the L point in the Brillouin zone, and you see that the position of the L point in the Brillouin zone is 0.5, 0.5, 0.5. We know that the gamma is the one that is in the center, and that's the reason why 0, 0, 0, because it's in the center. But it's not something that you define because you want to define. You go to the books and you get it. But again, like, don't worry too much about that, because you will never have to do that. Okay, probably. Or if you need to do that, like, you will need to check. You will know very well, because the experimentalist, somebody else will tell you, look, we're interested to know the band structure at the Y point, let's say, and then you will go to see on the Kittel book when the y point is in the Brillouin zone, and you calculate that, okay?
Or we just use what normally use, just like a number and a gamma and then the phi and the ferro.
For gamma, yes, if you're interested in gamma. And if you want other, let's say, if you wanted to see the L, yeah, then you can take these coordinates for the L, because these coordinates are not, let's say, made up by VASP. These are taken by like standard state of the art, like crystallographic.
You can also see that in the figure.
Yeah, you can, if you open the, exactly, if you open, like for instance, I mean, now we will take some times, and I hope we will not die so fast. So in case at one point the Zoom die, Mariam and Santiago, I will just generate the same one, so just enter the same, okay? Just in case, because I think that at one point,
okay,
it's not going to be a problem. So just to show you, because we can, okay, well, first of all, I can clear and close the annotation. So now, why doesn't clear? Come on. Okay. So also the correction here seems worse. Clear. Okay. Nice. So now I can make it larger. I can go to view. I can zoom in a bit, and then we go to the folder where we have the exam, because then it's going to be more clear what we just said. So now if you go to let's say Anson 2, then we go to 2.3, then we open the VASP run, and then now we go to electronic view key point. Okay. So now you see, no? So now this is the Brillouin zone. You start with the gamma point. You have 4 segments, the one that you define, and on each of these segments you have 10 points. Okay? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, and the first one 10. Okay? So the difference between the dose and the band is the density and also the structure of the key point. Because then if you take this one and then you go to key point, yeah, then you see that here you have a mesh. And you also see that like you have this kind of mesh because you're using the tetrahedron method. So you see that all your mesh is kind of condensed into tetrahedra that are probably also symmetric. Yeah, they seem symmetric. Okay. So just to, let's say, summarize the answer, the main difference is given by the mesh of the key points. Okay, and as a last thing that now I realized, so yesterday, like I was talking to you, and now I go back to annotate, that usually on the paper, we define something like a key point mesh, well, a key point density of like 0.03 angstrom to the power of -1. And yesterday, thinking about that, I just realized that the answer is very easy, okay? So this is the reciprocal space, okay? If you have a lattice vector of 30 angstrom, as I told you, then what happened, you should define for the Moskov path like a number of key points of 1, you know? And why is like that? Because from this lattice vector, you get that in the reciprocal space, the reciprocal vector that is corresponding to this one is given by 1/30. And 1/30 gives exactly 0.03. Okay? So then if you take one key point by 0.03, that means that you have like a density of key points of 1 key point every 0.03 angstrom to the power of -1 key point mesh in your Brillouin zone. Okay, if you take, for instance, 1/6, well, you take a lattice vector of 6 angstrom. Well, let's take it of 10 because it's easier to do. Then of 10, if you remember, like I told you, should be around 3. And it should be around 3 because, again, 1/10 gives 0.1. Okay, so that means that your lattice vector will have an extension of 0.1. Well, your reciprocal vector, sorry, will leave an extension of 0.1 angstrom to the power of -1. And then here you put 3 key points, 1, 2, So this last part was kind of clear already, or do I need to repeat the very last part? I mean, I can go.
Yeah, you can repeat the last part. You were talking about when you have 10 angstroms.
Exactly. So if you have 10 angstrom, for 10 angstrom, I told you that let's say of a given lattice vector, then I told you that you need to put 3 key points in that direction for the Monscore path. So like in the reciprocal space, so let's say this one will be like the real space. Yes. So let's put real, really badly written. Okay. And here instead is in the reciprocal space, the size of this lattice vector will be 1 over 10 angstrom to the power of -1. Okay. So this means that you have 0.1 angstrom to the power of -1. So that means that now you have a reciprocal vector that has a side of 0.1 angstrom. Okay. On this reciprocal vector, now you are adding 3 key points. So 1, 2, 3 key points. So that means that your key point mesh has an extension of the distance between 2 key points that became 0.03. Okay? Because that will be like the size of your lattice vector, so 0.1 angstrom to the power of -1 divided by the number of key points you're putting. Okay, that gives this 0.03. 0.03. This is really badly written, but hope you understand. Okay, so that is just the point. Okay.
But I don't understand what are you trying to point with that.
No, I'm not trying to point out anything. I'm just saying that like to say that you have a key point density of 0.03 angstrom or key point, no, let's better say a key point mesh with size of 0.03 angstrom to the power of -1. It's the same as saying that you are putting like 3 key points given a lattice vector of 10 angstrom. That is just, I mean, just to say that is equivalent, but nothing more, okay?
And the rule of thumb is based on that we want that 0.03.
Exactly, the rule of thumb is based that we are happy with that. Okay? Exactly. Because the point is that, for instance, if instead of 3, we would take 6, then this will be divided by 6. And so 0.1 divided by 6 will be a much smaller number. So it means that we are increasing the mesh that we have in the sense that we will have a larger discretization of our mesh. So more accuracy, but it's not needed. Exactly. Okay.
For me, I have no more questions.
Okay. Any point more?
About the Hansen.
Yeah.
We have for the demand. The that part, and we just have an example to know where is the optimum points, optimum lattice.
Okay.
From that, I took the number. I think it's 5.5. I think, and from that part, I have done calculation and have the number, and from that I also am interested to have the dose and find from that. But in this case, I use the key points from the FCC for comparison, and the key points from FCC and what I the present the figure of the dose is similar like what we have in the Hansen.
Yeah, what we show. So that in this case you are applying the tetrahedron method. In the other case, no.
Similar like this.
Okay. Yes.
Okay. But I also doing the P for Python, P for VASP with counter card. But in the counter card, it's zero number is out here.
Okay. Yes. Okay, I understand. Remember that when you want to visualize any property, you need to visualize them on the VASP. So you just open the concar if you just want specifically to see the structural property of your concar. If you want to see the electronic calculation, open directly the VASP. So I don't know why you see these problems. I mean, it may be, but I guess it's just an internal problem of Python for VASP because it doesn't read properly your the calculation, because you don't all the, let's say, all the properties of your system are stored in the VASP file.
Okay.
They are not stored in the concar. In the concar, you already opened the concar. In the concar, there are just the coordinates, okay? Plus some additional information on how like it was the previous step, but nothing more. So the problem is that probably like, yeah, Python for VASP is just put in there a random number or something like that. But like, it's just that you shouldn't visualize band or DOS on the concar, okay? Because you will not see anything.
Okay, and the other thing is when the second part, after doing the DOS, I also create a new band for calculate the band energy, and with the same key points come from the FCC file.
Okay.
And from that, I didn't obtain this. Or something similar like this, but it's not this.
Yeah.
I can't understand why it's because I just use the same key points.
Okay, okay, but wait a second. So we are talking about the 2.2 and the 2.3, right?
I mean the 2.4, the amount Gimbaco band.
Okay, so 2.4 and you created another one. Okay, when you check the band.
Okay.
Okay, yes, I understand. But the problem is that, you know, to do the band, as I said, like you need to have the key points that you define here or special kind of key point. Yeah. So of course, if you try to calculate the band with the key points that you use for optimization, you will not get a meaningful result. So that's the reason why. So in that case that you have in the Anson, the two, like the band gap that is showing and the other one, if you can give me, pass me just because then I double check. Yeah. So
I didn't have this.
Yeah, but the point is that, okay, so you need to remember, I mean, not you need to remember, like, since these Anson are not properly done, okay, maybe, okay, keep it because I'm going to share also for them.
I think I should do that also.
No, I show you what the problem is. Because, I mean, the problem is that because these Anson were done very quick, so there are some mistakes, but I think it's going to point them out to everyone.
Maybe I can show you what I have done.
No, I mean, I show you where the problem is because I think we'll solve everything. So here, like what we were talking about with Sichen is this part, okay, these two plots, okay? And I didn't open what I wanted to open because actually the problem is that on Anson 2, you get a wrong indication in the sense that they tell you in this line that, yeah, like, I think it's, okay, yeah, because I think that, you know, like it's telling you diamond C, okay, yeah. So what is the problem is that you don't get, so in Anson, what they want you to do is to, as you say, to generate two new calculations, but taking the key point of the DOS from the key points that you use for calculating the DOS of this FCC silica, and instead for calculating the band, you need to take the band, the key points that you use for the band. So did you do that? Did you use like the key points that you use to calculate the band structure here?
Yeah.
Okay, and you don't get exactly the same as it.
Exactly the same, but what I have in the figure is very similar like the FCC, like this. And but it's not like similar to the what the diamond should be.
Okay, I see. So let's go to see very quickly, like the simulation. Yeah, I will do that just now. So, okay, so that means that we are here. Then you do 2.4. Okay, band, yes. Okay. Then here.
Use the
yeah, this is exactly the same. Okay.
It could be used the same, or should I create a new one?
I mean, in principle, it's okay. So, okay, but then, okay, the run is okay, and then the incar. Okay, the incar is
I use the incar from the FCC because I think it's the same thing.
Yeah. Let's see. So now I will open the VASP run.
So this is your VASP that I just copied. So electronic. This is our electronic. Okay, this is okay. Yeah, this is the proper one, and then we go to those
it's not same.
Yeah, it's the same, no?
A little different because the from the 80s and the UK part, there's something different.
Okay.
I don't know why it is.
Wait. I think we need to. Okay, let's put it like in one side and the other side because we cannot see. Okay, so the difference is the UQ, no?
Yeah.
Okay, it's the UQ and UQG. Okay, let's check the key point. Okay, so the key point that you put, UQ. Okay. Yeah, okay, I see. Yeah, I think that the problem is that even though they are telling you, like you see like that, in this calculation that they did, they added a new segment. So they have an extra segment, okay? So you see that in your case here, like what we define on the key point is like 1, 2, 3, 4 segment, okay? In the graph that they have here, they have like 1, 2, 3, 4, 5. So that's the problem. So the reason why you don't see this point in the middle is because you are not adding this segment. So if you want to have exactly the same graph, you need to modify this. So you need to modify your key points. And okay, LG you have, XU, well, GX you have, XU you have, and then you see that you have like UK, there is not a segment in between.
Oh, okay.
So if you want to generate this, then you need to add one line with these two. So like you add one line with these two, you run your simulation and you will get exactly the same. Okay. But I mean, like, yeah, I forgot actually that on the Anson, like you needed, they also told you to calculate the band and the dose, repeating it. So yeah, I mean, I didn't point out the last time because actually it's not that important because it's exactly the same calculation as the other time. Okay. And it's not that meaningful. Okay. So yeah, if you want, you can just add 1 and 1 and then will work. Okay.
And what does the relaxing the structure mean?
Optimizing the structure mean.
What does relaxing the
Okay, every time you see a relaxing means optimizing. It's basically the same thing. So exactly. So to relax it, if you want, we can see it. To relax the structures mean that, let's see if I have a bad like bulk to show you. Means that, for instance, if you take the bulk of these, okay, this one should be okay. Let's take the first one. So this is like a bulk that you get from the crystallographic things. Okay, is rather packed, you see, and is also rather big, much more complex than the one that you use. So, okay, actually I can, well, no, let's leave it here so that you can also see. So if now what I do, I go to like relaxation and I started like, I put the speed and I put the play. I mean, you see now that it's changing. I mean, it's very fast, so you cannot really see. But here I'm applying this ECF algorithm. And every time you see that it's changing the lattice vector. Now it's stable. Now it's moving a bit the atoms. Now it seems happy with this, and then it reduces again. Okay. So what it means to optimize a surface or a structure means to change either the position of your vectors or your lattice constant, or and so the cell volume, so that you can get to the lowest energy configuration. Okay.
Just change the volume.
Yeah, I mean, yes, because here you are using, like here, what you want to optimize is the lattice constant.
And the way to optimize the lattice constant is by changing the volume. I mean, whenever like you adapt the lattice constant, you're also changing the volume, exactly. But why you, like, the point is that you start changing the volume because the first, like, usually these bulk are already pretty optimized. So you don't see that much motion inside the atoms. But if we like zoom, you may also see some like very small like movement of the atoms, but they are really small. So you cannot really see them, you know, because what to optimize simply means that you see this arrow. So these are the arrow of the forces internally that you have in your system, okay? So what you do when you relax, you try to lower these forces. So for instance, you see now that you have a lot of forces, okay? Because these two like atoms are too close. So if now you start optimizing, you increase the volume. So that means that this distance become bigger. So since the distance becomes bigger, you see that you don't have anymore that much forces. And then you keep doing that, trying to minimize the forces, because if you minimize the forces, then it means that your surface should be more or less stable. And then you get to the lowest energy configuration, okay? So in this case, you see that this system is not that well defined because it started with a really positive energy, because the lattice vector that we were taking from this metallic database was bad. Then you see that we go till -60 because it means that larger, like we are going to a physical structure more or less. But then you see that at the end we are still going up. So here there is a problem of convergence in general, okay?
And we need the interaction between the two atoms become smaller.
You need to minimize the forces in your system, because in general, you know, like in every system, like the system that stay at equilibrium is the one with the lowest forces, with the lowest residual forces. Okay, so if we are sitting on a chair now, it's because the force of gravity is minimized because we are on a chair, you know. So that's the point. Like these are just basic like Newton law, you know, that like for, well, actually this is quantum mechanics, but still like for the system to be in the lowest energy configuration, you want to minimize, because you see, like to be in the lowest energy configuration means that the system should be happy to be there, you know. And if you put two atoms that are too close by, I mean, they will repel for sure. So if they repel, that cannot be the lowest energy configuration. It means that your system is not stable, but you want to have a bulk that is stable, okay?
So we need to do just
yes, exactly. So the optimization is because you want to have an optimized bulk, because in reality, the bulk that you see should be stable. I mean, if you see a piece of copper, the reason that you see that is because it's stable under room temperature. If a bulk is not stable, then you don't see it because it's unstable, because it will decompose to other things. Okay. And since experimentally you work mainly with stable things, we also need to get the stability of the structure. Okay.
To have the minimum energy.
Exactly, to go to the system that has the minimum energy. Okay. Yeah. Any extra points, since it's already 11:24? I mean, it's already later, but I arrived late, so there is no problem. Here? No. So Santiago, Mariam?
For me, everything is clear. So
okay, good.
I have no question.
Mariam still needs time to, well, need the firewall to be set, so she like, I guess she doesn't have much. Good. Then,
thank you, Federico. Everything was clear.
Good. Yeah, then I think that we are done. Okay. So yeah, like keep working on that. And yeah, just like two general comment that I did yesterday. So like this tutorial, well, I did yesterday part of them, and then like now I'm adding some of them. These tutorials are not meant to give you all the solution, because otherwise they will be called solution. This is just meant to give you some input to solve the problem yourself. And in case you don't manage something, like this is not a test, you know, I mean, it's not that on Thursday we decide who is good or who is bad. It's simply that then we can correct directly all the exercise, you know, because at the end, like, I mean, we are all researchers, right? And we know that in science, it's not that there is a good solution or a bad solution. There are just different solutions, and some of them may work, some other may not work. But the reason why sometimes, you, like, let's say, after the tutorial, you should still have some doubt, is because otherwise somebody else is doing the work for you, you know? because at the end you still need, you still need to challenge a bit yourself, because otherwise it will be too easy. Otherwise I could just give you directly all the input prepared, you run them in like 3 minutes, but then you don't get anything. And then the last thing that I was not telling to Mariam, but I was telling yesterday to Santiago, Sichen, and Enrique that was in the room. They were just some tips for like the scripting part. That is basically like, have you ever scripted anything, Mariam, before? Like any Python? Okay, cool. So that's the reason. Since also like other people didn't, like Enrique didn't much, also Sichen, I also didn't before I entered the group. What is the most important part is that whenever, like for sure, all the information is online. So whenever like you have a doubt, you can just look on Google and there will be a solution, usually many more than one. But the most important part is just that if something doesn't work, it's much better to close the computer, do something else, and then you come back to that the next day. Because programming is not really something that more time you dedicate, better it gets. It's actually get the other way around. It is better just to disconnect, because then with like the brain that is a bit more calm, you get to solution. Okay, so like if something doesn't work, just rest, all of them. Yeah, so I think that like if there is no more, like we are done. And since I have the slide open, I think I will just remind you like the next moment that we meet each other. That will be exactly on Thursday, okay? So we see each other on Thursday at 10 in the E4, and then we will do everything in the E4. Okay. Good. So yeah, thanks for like.
Okay.
Yeah.
Thank you very much.
Thank you, Fede. Thank you, everyone.
Have a good day, all of you.
See you. Bye-bye.